So I'm going to skip doing Theorem 52 in the lecture, at least the proof of it, but I hope you will read that when you do your reading. And the statement is pretty nice, so it's a useful thing. A way of thinking about the range of a function. So if you know f is a function, so remember domain and range, these ideas, we define these before we define function, right? So we can talk about the domain and range of any set of pairs, even if it's not a function. The domain just picks out the left-hand positions of all the pairs, and the range picks out the right-hand positions. But if you do have a function, then there's other ways of thinking about things in terms of function evaluation. So if you are looking at a function, then for something to be in the range is to say that it's f of something that is in the domain. So for y to be in the range is exactly just saying y is f of something from the domain. So you can think of, this is telling you that you can think of the range of f as the set of outputs when you input things that are coming from the domain of f, where the domain is the set of inputs, the range is the set of outputs. And this also shows you that being in the range of a function is this kind of existence statement. To be in the range is to be f of somebody. There exists something that you are f evaluated at. All right, so that I'll let you look at on your own. Theorem 53, I'm also not going to prove because that one is one of your possible presentation choices. And this is a really fun one, I think, to prove. The reason I'm bringing it up here in the lecture and focusing on it is that it actually provides us with another way of proving equalities in some situations. So right now, if I ask you to prove an equality, like if I just say, I define some set A equals blah, 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 and B equals blah, 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 and then I say, okay, now prove A equals B, what would you do? What's your gut reaction? Hopefully, your gut reaction by now is prove A is a subset of B, and then prove B is a subset of A, right? So hopefully your gut reaction is use Theorem 10, prove two inclusions, and then that will give you an equality. Theorem 53 is providing you with an alternative. It's saying sometimes you have this alternative. If these things are functions, so if instead of giving you some random a and b, I gave you f and g, let's call them, which are pretty nice names for functions, and there's still some sets, but suppose you knew they were functions. Then I ask you, okay, now prove f equals g. What is a way to do this? Well, before having Theorem 53 available to us, you would do it by proving these two inclusions, right? F is a subset of g and g is a subset of f, which is actually what you will do to prove Theorem 53 here. But once Theorem 53 is available, you have this other way. Theorem 53 says if you know f and g are functions, then one way to prove that f equals g is to prove that their domains match up and that they always have the same output for any given input. So hopefully that's intuitive to you also, like that's intuitively what it feels like for two functions to be the same. And Theorem 53 is basically telling you that is a valid way to prove that two functions really are the same. Now, when you go to prove Theorem 53, like if you choose this as your presentation problem, then the way to do it, so it's an if and only if, so you'll have two directions, right? And the hard direction will be trying to prove that f equals g, given this stuff, right? So you'll assume this stuff, and then you'll try to prove f equals g. When you're doing that, of course, Theorem 53 itself is not available to you, so you basically have to do it this way, by double inclusion. And that will be interesting, connecting this like a very set theoretic, very set way of thinking about equality, and connecting that with functions as these input-output machines. Okay, and I want to, before ending this lecture, I want to go at least up to here and define mapping notation, because this one, Theorem 55, is going to be your homework problem to prove this one. So your written homework is going to be this one. Okay, so let's have a look at definition 54. So this definition is really introducing a new notation, and here's the way that notation works. I usually call it the mapping notation, and it consists of a colon and an arrow and a bunch of stuff. So there's a colon and there's an arrow, and you can put any term here, and any term here, and any term here. And then what you get overall will be a proposition. Excuse me. So what you get overall will be a proposition, and that's kind of different from our usual pattern for the last few definitions, where you put a bunch of terms together and you get a term. So this is a proposition. So that means it asserts something. So this will say something. When we say f maps x to y, which is how you read this, f maps x to y, this is a sentence. In fact, it sounds like a sentence when you write it out in English. F maps x to y. It has a verb, maps. So think of the arrow as a verb, and you can put a period at the end of this, right? So this is a sentence, you could put a period at the end of it. This is not an object. It does not refer to an object. Okay, but this is a weird one where sometimes people do take it to also, sometimes people use this notation to also refer to the object f. So sometimes it is used to refer to an object, but you can forget about that and then just look at that extra usage, extra grammatical usage as it comes up later on. For now, this is a proposition. It says something. Okay, so what does it say? The idea, semantics, the idea is that it says, so maps means it's saying f is a mapping. That's another word for function. So f is a mapping is another word for function, where we think about functions as mapping inputs to outputs. So like if x is an input to a function, little x here, not capital X, if little x is an input to a function, then we think of f of little x as an output. And we say things like this: f maps the input little x to the output little y. Okay, but that's going to be a confusing thing to write down, considering that now I'm going to talk about things at the level of sets rather than the elements. So f is a mapping from. Let me phrase it this way, actually, in terms of elements. F. When we say f maps x to y, that's really short for saying f maps the elements of x to elements of the set y. So, in other words, f associates to each element of x a unique element of y. In other words, f is a function, and the elements of x are all valid inputs for f, and they are all the valid inputs for f. And the outputs are always going to be elements of y. So here's how to say that in terms of our formalism. When we say f maps x to y, we are saying a few things. F is a function, first of all. That's what I mean by it's a mapping. It associates inputs to outputs. And what are the allowed inputs? So when we're talking about a function, the kinds of things you can input, so let me look here, where any of this stuff works is things in the domain, right? Something has to be in the domain for us to be able to talk about f of x. Or I should look at the definition. When f is a function and x is in the domain, that's when I can start talking about f of x, and then I start calling that an output. So what is the domain? Well, this assertion is an assertion that capital X here is the domain. The domain is capital X. So when you write this, this is a quick way to say something that we say very often. We very often frequently have to write this phrase, f is a function and this is its domain. This is a quick way to do it with symbols. F is a function and x is its domain. And it assigns a nice name to the domain. But there's another part to it, which is the y part. And you might think that this is going to say range of f equals y, but no. It says range of f is a subset of y. And if that bothers you, just wait. eventually you will see that this is a good way to define the notation. For now, I will just say that typically when you define a function, it's hard to say anything immediate about what the range is. Usually you can say something immediate about the domain because you chose that when you define your function. But the range is something you have to deduce afterwards. So it's kind of hard actually to say what the range is. And so it's nice to have this notation not require us to know the full range. Only requires us to know about a set that contains the range. And finally, for LaTeX, if you want to write in math mode, f maps x to y, you just f colon x, and then here you can do 2 for the arrow, \2. You can do \right arrow, but with the r not capitalized, so that it's an arrow. It should be an arrow like this kind of arrow, not an implication arrow. Just like that. And of course, after right arrow, you should put a space so it doesn't think that that's part of the command. Yeah, so that's all. So that's the mapping notation. So it's this quick, convenient way to say a bunch of things. Write these symbols, and then immediately you're saying f is a function. I'm assigning this name to its domain, or maybe if this is an already known thing, then I'm asserting that that is the domain. And here's where the outputs are going to live, although it might not be all of them. Or rather, it might the things in y might not all be possible outputs. And your homework problem is going to be another way to characterize what's going on here. So you'll show that f maps x to y if and only if these two conditions hold. F is contained in this Cartesian product, so meaning all the pairs in f have their first position in x and their second position in y. So to make any use of this, you'll have to somehow use probably essence of Cartesian product. And x is a subset of the domain of f. So this is sort of another way of framing these three conditions, is you can write them as these two conditions instead. Okay, and as is becoming usual now, I'm sorry for letting this lecture run so long. In the next video, I'm just going to go through some examples of using this notation, and then I'll call it a day.